Hello again, and we are now on lesson 3 of limits, where we are going to talk about the idea of continuity, something being continuous. And again, this is one of those things that has nuance, but there's also a bit of common sense here, so don't ignore your common sense as you go. So let's talk about continuity, but let's just talk about it in a generic sense for a second. So if I draw a graph of a function, and it looks like that, and this is like x equals 3. This function f of x is not continuous at x equals 3, because continuous basically means like doesn't stop, and this stops, it's broken. So this graph is not continuous at 3. If I were to draw another graph that looks like this graph is also not continuous at 3 because it goes to 3 and then like disappears for a second and then reappears and continues afterwards. It's not continuous at 3. Now, if I took that one and I colored that dot in, that would be continuous at 3. And that's continuity in a nutshell. Continuity in a nutshell is if you draw a graph of a thing, and you can draw it without picking up your pencil, it's continuous. This is continuous. This is continuous. This is not continuous. This is not continuous if that other red thing didn't exist. If you have to stop drawing for a moment, then it's not continuous when you stopped drawing. Okay, so now let's talk about what the heck does that mean, though, in a real sense. Let me delete this. All right, so continuity. At an interior point, meaning inside of an interval, a function y equals f of x is continuous at an interior point c of its domain if the limit as x approaches c, which again remembers that you're considering c from the left and c from the right. I said that in a different order than I wrote it, but you got me. C from the right and C from the left. If the limit from both sides equals the function value, then it's continuous. Okay? At an endpoint. Now, we have functions that don't have a left side and a right side, and so we don't want to be ridiculous about it, so let's consider something like this graph, which is y equals the square root of x. If I wanted to know if y equals the square root of x is continuous at x equals 0, if I tried to come from the left of 0, I can't because the function doesn't exist over there. If I approach 0 from the right, that works. But if you have a function where the function starts at a specific x value and it has nothing else to the left side or the right side or something like that, just ignore the other one. So this second part where it says endpoint, a function y equals f of x is continuous at a left endpoint A or at a right endpoint B if the limit from the right equals the function value or the limit from the left equals the function value. In other words, it doesn't have to be connected on both sides if one of the sides just isn't there to begin with. All right? Now, technically, they write continuity as two conditions, that the limit as x approaches c equals f of c. But I want you to really consider 3 conditions and not 2, because this really has 2 parts, and those 2 parts are these things right here. Something is continuous if you approach x toward b from the left, and x approaches b from the right, and the function value at b, if all 3 of those are the same, then the thing is continuous. And here's how that looks. It basically says, if I have a function, f of x, and here's x equals b, and if I come at b from the left, and b at the left equals some value, and then if I come at b from the right, and I equal the same value, and then I say not only that, the limit from the left and the limit from the right match up, but I guarantee you that that dot is filled in, then that function is continuous. Okay? And then graphically, something is continuous at x equals c if you can draw f of x in the neighborhood of c without picking up your pencil. All right? Continuity is relatively common sense, except for the minutia of remembering that continuity has a limit definition. The limit from the left equals the limit from the right equals the function value. That's where continuity comes from. So example 1 says use the definition of continuity. That means using that limit. Use the limit definition of continuity to determine if f of x equals that fraction is continuous at x equals 3. Oh man, got another absolute value. If you remember in the last video, absolute value and calculus do not really like each other. So I'm going to rewrite f of x, which is really 2x minus 3 in absolute value over x minus 3, is really a piecewise function where sometimes you leave x minus 3 alone, and sometimes you negate x minus 3. And you say, okay, x minus 3 on the inside is already positive when x is greater than 3. And x minus 3 on the inside is negative when x is less than 3. Okay? Now what about when x equals 3? Oh, x can't equal 3 because the function doesn't exist at 3 because I'd have a 0 on the bottom. Okay, cool. So then this says use the definition of continuity. All right, so the definition of continuity says take the limit as x approaches 3 from the left and see what you get. Okay, well, let's see. If x approaches 3 from the left, then that's when I'm less than 3. I'd plug 3 into here. These x minus 3's effectively cancel out, which means that's 2 times negative 1. That's going to be negative 2. All right. Now if I let the limit as x approaches 3 from the right of f of x, from the right of 3, that's when x is greater than 3, which means I'd plug into here. These cancel and divide to 1, so that's 2 times 1 over 1. That's 2. And then f of 3 does not exist, because if I plug 3 into here, my denominator is going to be 0. So f of 3 doesn't exist, or you can write f of 3 as undefined. And so I would say f of x is not continuous at x equals 3 because the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right, which also in this case does not equal f of 3. Now, if any pair of those don't equal, you don't need to, connect it to the third that's still not equal, but I'm trying to emphasize a point here. All 3 of those need to be the same, and in fact, none of them are the same. So this is very much not continuous. All right. Example 2 says, use the definition of continuity to determine if g of x is continuous at negative 3. Okay, fine. Well, definition of continuity, around negative 3, the limit as x approaches negative 3 from the left needs to be compared to the limit as x approaches negative 3 from the right, needs to be compared to g of negative 3. If I want to define continuity, and I don't have a graph, so I can't look at it or anything, I got to test these out. All right, negative 3 from the left, so that's less than negative 3, which puts me right here. And if I plug negative 3 into that, I'm going to have 9 minus 9 over negative 3 plus 3. I'm going to have 0 over 0. But wait a second, I'm taking the limit. And if a limit goes to 0 over 0, I got to do a little bit more work. So man, I got to come down here and say this is going to be x plus 3x minus 3 over x plus 3. So the limit as x approaches 3 from the left of g of x really means I'm plugging negative 3 into x minus 3, because that's what this simplifies down to. And that's going to be negative 6. Okay, that was a lot of work. All right, now I need to compare that as x approaches negative 3 from the right. Negative 3 from the right means bigger than negative 3, so I'm using the bottom expression. If I plug negative 3 into there, I get a very easy one-step negative 6. Awesome. And g right at negative 3 is the middle. At negative 3, that's negative 6. Hey, look at that. All of those are the same. So g of x is continuous at x equals negative 3 because the limit as x approaches negative 3 from the right equals the limit as x approaches negative 3 from the left equals negative 3, which, just for added benefit, is negative 6. And all of those things are the same. Therefore, g of x is continuous. Cool. All right, number 3. Now we have a graph. Okay, don't have to deal with algebra. Great. For which values of x is f of x not continuous? So graphically, continuity is super easy to spot. It's basically, if you were drawing this, when would you have to pick up your pencil? So it is not continuous when I pick up my pencil, go down, make a circle. All right, so I picked up my pencil at x equals 1. Draw a dot, go over, draw a circle. I pick up my pencil at 2. Go up, draw a dot, go down, draw a dot. I didn't need to pick my pencil up for that. So it's continuous everywhere else. So for which values of x is f of x not continuous? X equals 1 and x equals 2. It did not ask me to justify using a definition, so I'm not going to. Now, with all of these discontinuities, places where it's not continuous, those discontinuities can be labeled as removable or non-removable. A removable discontinuity is where there's a hole that you can just fill in to make the function continuous. So for example, and I want you to draw this, if I have a graph that does one of these, that's a removable discontinuity because I could just come in here, plug the hole, and be on my way. That is a removable discontinuity. A non-removable discontinuity is if you have a hole and then you either have a hole or a dot and it's somewhere else and it's broken, like straight up broken. Or maybe if you have an asymptote where you have a graph that does this. That would also be non-removable, okay? That's the verbal and graphical definition. The algebraic or numerical definition of removable versus non-removable has to do with the limit. If the limit exists but does not equal the function value, either because the function value is another number or because the function doesn't have a value there, then it's removable. So if the limit goes to 4 but the function equals 7, that's removable discontinuity. But if the limit doesn't exist, that means the function is so broken that you can't fix it, and that's a non-removable discontinuity. Okay, so like up here on example 1, my limits went to 2 different values. Therefore, this would be broken if it were a graph, and this would be a non-removable discontinuity at x equals 3 because the limits of the 2 different sides don't match up. All right, so it says classify the discontinuities for each of the last 3 examples. All right, so I just did that. This would be non-removable discontinuity. This number 2 was already continuous, so I don't have anything there. And then down here, if I get rid of my scribbles, let's see. At 1, my graph is very broken. So this would be a non-removable discontinuity. 2, it is connected on both sides of x equals 2. So if I just like move this dot down here, it would be continuous. So we call this one a removable discontinuity. Removable, yep, because the limit exists, but the function doesn't match the limit. All right, on to the back. Well, if it's removable, then let's remove it. That's what the back is, creating continuous functions when they're not maybe continuous yet. So remember, to force a function to be continuous, both the one-sided limits must approach the same value and the function's got to equal that value. So example 1 says f of x equals a minus 4 for x is less than 2, and x squared for, x squared for x is greater than or equal to 2. We're going to go to the land of Desmos to do this. So here's my Desmos, and my function is ax minus 4. And I'm going to add a slider for a, and that is only going to work for x is less than 2. And because I'm fancy, I'm going to make this 2 comma f of 2. And just so you can see the hole there. Now you can see that hole. All right. And then it is x squared for x is greater than or equal to 2. I'm just going to call it g of x to make my life easier. So there's that. And then this is going to be 2g of 2. And there's a dot on that one. So if we look at this, it's not continuous right now. The question says, find an a that makes it continuous. Watch this. This is really cool. Ready? Whoop. So I want to figure out what is that a value that's going to connect the dots. Well, it looks like it's a equals 4. That's kind of cool. But graphically, that's what we're doing right now, is we're saying I have a line and a parabola and I want them to touch. How's that going to happen? Back to the notes we go. So it says find the value of a so that f of x is continuous. Okay, well if something is continuous, the left side and the right side need to meet. Well, that means ax minus 4 and x squared need to meet, and they need to meet where the graph is broken, which is at x equals 2, which means 2a minus 4 needs to equal 2 squared. Add 4 to both sides, so 2a equals 8. Divide by sides by 2. For a equals 4, this is continuous. That's it. The next one says connect the parabola to the dot to the line. Find a and b so that g of x is continuous. Okay, so I need 2x squared minus ax plus b to equal 6 to equal ax plus b, where all that stuff is broken at x equals 3. Let's just deal with 2 things at a time, shall we? So let's see, at x equals 3, that's going to be 2 times 9 minus 3a plus b. That needs to equal 6. And at x equals 3, 3a plus b needs to also equal 6. Okay. Well, that's 2 equations, but I also have 2 unknowns. So this is a system of equations. And now I just need to find a and b. So let's see, I'm going to take this first one. I'm going to subtract 18 from both sides. So negative 3a plus b is negative 12. And let's go for substitution. So that would mean b is negative 12 plus 3a, right? So I'm going to move that b, give it to this side, and say 3a plus negative 12 plus another 3a equals 6. 6a would need to equal 18 if I add the 12 to both sides and combine the 3a's. So a is 3. And if a equals 3 goes back into here, b is negative 12 plus 9, which is negative 3. And there's that one. Three says h of x is k for x equals 5, and the square root of x plus 1 minus 4 over x minus 5 for x does not equal 5. Find k so that h of x is continuous for all values on its domain. Do not write this down. Red means stop. So if I were just plugging and going along, I would say, all right, so then k needs to equal, again, red means stop, don't write this down. X plus 1 minus 4 over x minus 5 at x equals 5 where it's broken, and then I put the 5 in, and I get the square root of 6 minus 4 over 5 minus 5, and that's undefined. And I'm also realizing that I made a mistake here and that we're going to fix it together. So there's a couple reasons that we need to stop here. What mistake did Mrs. Vibber make? I think the mistake that Mrs. Vibber made was that that's not supposed to be x plus 1. It's supposed to be 3x plus 1. That'll fix it. All right, so thing number 1. I made a mistake. That's supposed to be 3x plus 1. So this would be 3x plus 1. And this would be 15 plus 1 right there. So everybody go in, put a 3 in there. My apologies. All right, even still though, here's the problem and here's why it was red in the first place. When I look at this red stuff, the square root of 15 plus 1 is the square root of 16. 16 minus 4 is 0. I get 0 over 0, and k is not undefined. That's not the right answer here. So here's what this one is invisibly saying. It's saying you have a graph that when x does not equal 5 has a hole in it. You have this expression, this quotient, that when you graph it has a hole in it right at 5. What value of k plugs in the hole? So instead of doing this one, like I did in red, we're going to back off and say, listen, this isn't so much piecewise as it is a function that wants to be continuous but just has one little teeny tiny missing dot on it. How do we fix the dot? And here's how we do it for real. Okay, so let me delete this. Whoop. Okay, so I have this over that, and I want you to write this down. And when we plug in 5, we end up with 0 over 0. And 0 over 0 means that something that's the same happens on the top and on the bottom. I just have to make it reveal itself through like canceling and multiplying and stuff like that. So I have a yucky looking expression with a radical on the top. I'm going to rationalize the numerator and see if that helps. And you may be thinking, but Mrs. Vibber, how do I know when to rationalize the numerator? And the short answer is you don't. The long answer is if you get 0 over 0, somebody's got to cancel. And if you don't notice that they can cancel, you need to start manipulating the way it looks until it reveals itself. And rationalizing is one way to get there. All right, so I'm going to multiply that. And if I distribute on the top, I get 3x plus 1 minus 16. And in the bottom, I get x minus 5, 3x plus 1 plus 4. And so then my numerator would be 3x minus 15, which is really 3x minus 5, which really means I need to figure out what happens as I get near, but not equal to 5, on the expression 3 over 3x plus 1 plus 4. This is difficult, okay? I'm not going to sugarcoat it. This part's hard. So you have to first realize that sticking the pieces next to each other with an equal sign, not going to work for you. Then you need to realize, oh man, I need to rationalize this. Okay, fine. And then after rationalizing, you need to realize, wait, I was trying to figure out what happens near 5. So now I'm going to plug 5 into here, and I'm going to get 3 over the square root of 16 plus 4, which is 3/8. So if the limit near 5 goes to 3/8, that means if k equals 3/8, I'm going to plug the hole that technically exists there. Okay? All right, very last one. If the limit is x approaches c of f of x equals L, where L is a real number, which of the following must be true? I'm going to start sewing in some multiple choice here because math exists in 4 places. Algebra land, graphical visual land, chatty land, verbal explanations, and numerical land. You need to be able to connect all of those to make things make sense. So for me, when I read this, as x approaches c, the limit exists and equals L. That tells me that I have a function that near x equals c has a limit that goes to L, which means it does something like that. Since they only told me about the limit and not the function, I don't know if there's a hole at the point CL or if there's a dot at the point CL. So all I'm guaranteed to have when a limit exists is a hole that's connected on both sides. So it says, which of the following must be true? Does f have to be defined at c? There might be a hole there. Just because the limit exists doesn't mean the function exists. B, f of c equals L. Well, no, the function doesn't have to be defined. There just needs to be a hole there. C, f is continuous at c. Well, this isn't continuous. None of those have to be true. If a limit exists, it means that you approach a point from both sides, but that point might not actually be there. It might just be a hole. Okay. I am done with this video. So you made it through 3. 3rd time's the charm. Now you're used to videos, and everything from here will be fine. I hope you are all having a glorious morning, afternoon, evening, middle of the night, bus ride into school where you realized, oh my gosh, I forgot to watch that video last night. Whatever it is, I hope you're doing well. Toodaloo, kiddos.